All right. Yeah.
So Ali, just a second. So I would just want to welcome everybody to session 4, knowledge representation of our conference. Today we have 5 presentations, 3 long and 2 short. So if you are presenting a regular paper, you have 20 minutes for your presentation. If you're presenting a short paper, you have 8 minutes. When you're presenting, I will turn off my camera. I will count the time, and the last minute I will pop up. So if you see me popping up, you know that you have 1 minute to wrap up your presentation. If you have questions, we are going to address all the questions at the end of the session. But if you have questions, I encourage you to use the chat. Sometimes we forget the questions when we watch all the 5 presentations. So please feel free to use the chat or to write in a notebook, and then we address them later. So I'd like to welcome Ali, our presenter of our first paper. Good luck, and I'll be gone for now. Thank you.
Thank you very much. My today presentation is about a way in clustering social networks. We have proposed a way for clustering big social networks. It's non-negative matrix factorization and independent component analysis for clustering social networks. I am PhD candidate at the University of Windsor, and my main research interest is representation learning, and my secondary research interest is privacy preserving in machine learning. As you all know, clustering a social network is a way to better understand the network group nodes according to the characteristic of the nodes. In a way that similar nodes with specific characteristics are grouped into one cluster. One way to classify the nodes is to categorize them according to their specific characteristics, and then we can recognize each node by using their groups. There are 2 important metrics in social networks by which we can measure the clustering quality. The first one is modularity, and the second one is Sylow coefficient. These are 2 well-knowns, and there are others like conductance and others, but these are 2 well-knowns that have been used in many approaches. The first one, which is modularity, is a bit old, and the second one, Sylow coefficient, although it has high computational overhead, but it's more accurate. For example, in this graph that you see here, because it is similar, the way it's been clustered is similar to our expectation, to the human expectation. So when we compute the modularity for this graph, it's going to be 34%. But when we compute then measure the clustering by Sylow coefficient, it's going to be 63%. So we can conclude that Sylow coefficient seems to provide better measurement for such clusters in social networks. So we will go forward with Sylow coefficient for our experiments. Okay, let's start a bit about literature review. There are various ways to do the clustering of social networks. Some of them are focusing on improving the modularity, like K-means, low-weight, and hierarchical low-weight. Some of them are focusing specifically on Sylow coefficient improving, which, as I said, is computationally intensive and requires high computational capacity, like the hierarchical clustering and Sylow SCD, or Sylow community detection. And the third one that are the approaches that neither use Sylow coefficient nor modularity in their approach, in their measurements, but they use other modularities like conductance in their approach. So the example for that is multiple local community. Okay, let's go to our work and see what's been done in our work. Imagine that we have a cluster, we have a social network that we need to cluster it. We will do some steps in each step. We'll do specific function, and I'll go through each of these steps in the next slides. And these are the building blocks of our work. In the first step, we are going to find we are going to change the format of the social network such that we can use less memory in our computation. In the pre-processing step, we are going to change the adjacency matrix to the CSR format matrix. CSR stands for compressed sparse row matrix, so that we're gonna use less memory in big scale networks. For example, when we have a network with 1 million edges, then if we use adjacency matrix, then we will use a lot of space. So we can convert it to the sparse matrix so that we can proceed the processes and use less memory for that. The second stage that we do is a main stage, which is NMF decomposition. NMF usually non-negative matrix factorization decomposition. It is used for decomposing a matrix into two separate matrices. These matrices are called feature matrix, which is W, and importance matrix, which is H. The dot product of these two matrices results the original matrix. So in this step, we decompose the original matrix into two matrices and use each of these matrices in our work to do the specific approaches. The next step in our approach is ICA transformation. We use ICA transformation for dimensionality reduction. As I said before, silhouette coefficient is computational expensive. So when we use a big social network with a lot of clusters, with a lot of nodes to compute the silhouette coefficient, then we need to tolerate a high computational overhead. So in this case, in ICA transformation, we are going to reduce the number of features. In this case, when we reduce the number of features, then we will have less features for the silhouette computation. So in this, we can proceed with silhouette computation with less computational overhead. So at this specific step, we are going to reduce the number of dimensions from L, which was the original dimension, to C, which is the very smaller than the original dimension. So at this step, we simply change the dimension using independent component analysis, and we will go forward to our next approach, which is our proposed k-means approach. The proposed k-means approach is, we have introduced a new k-means approach based on NMF, which is, we generally are going to initialize the centroid such that the k-means performs better. We initialize the k-means using the importance matrix that we already had, and also in order to initialize, in order to cluster the W matrix. In this slide, you will see that how we do the centroid initialization in the k-means. As you can see here, the first step, we need to clip the centroids such that according to the edge matrix that we have, we need to clip clip edge in order to initialize the centroid, and then we send this centroid, this newly found centroid, to the conventional k-means. to find the cluster, to find the appropriate membership and clusters. So at the end, we end up with some labels. After K-means is done, the centered initialization is done, and we did the clustering. We will be done with some labels. Using those labels, we can compare the original matrix, and those labels, we can compute the silhouette coefficient, and we end up with the outputs. So this was the overall scheme of our work, and we will go through the experiments in this slide. We have done the experiments on four different data sets. As you can see, each of these data sets have different number of edges, different number of nodes, different complexity or triangles. These are very well-known data sets in the social networks that we can use. We have set the number of clusters from 2 to 10, and the set of components for dimensionality reduction from 50 to 100. So according to these data sets, we have done our experiments, and here is the results. As you can see, for the data sets that provide bigger edges, it means that the higher the complex data sets means that when the CSR matrix gets higher, for this kind of data sets, we will have a better improvement. For example, in YouTube, which has already 1.9 million edges, we will see the better results. And in the next big data set, which is academia, we will see 1.4 million edges. We will see the next better results. So in this case, we can conclude that, according to these experiments, we can conclude that the higher number of edges in the data sets will result in the best clustering comparing to the k-means. When we do the k-means, when we compare with k-means, the more the edges, the more the best silhouette coefficient we will see. So let's go through the other experiments. This experiment is done comparing to MLC. We have provided another approach for comparison with MLC. Because MLC has its own internal mechanism to find the best number of clusters, we first found the number of clusters, the optimal number of clusters using MLC, and then we fed our work with this number of clusters. For example, in MLC, YouTube was the value for YouTube was 5 clusters. For Facebook was 4, for Twitter was 2, and for academia it was 2. We fed this number of clusters into our algorithm to see the results. As you can see, the results are very in terms of silhouette coefficient, we performed much better than MLC. MLC internally uses a breadth first search, and it's not going to optimize any kind of measurement, as I told you in the earlier slides. So as you can see in this slide, we have improved much better in terms of silhouette coefficient comparing to MLC. The next experiment is done on hierarchical Lowane. In hierarchical Lowane, likewise MLC, we have found the optimal number of clusters using this Lowane, using this clustering approach for each data set. For example, we found 136 for academia and so on and so forth for each of these data sets, and we ended up with these silhouette coefficient. And after all, we fed our approach with the optimal number of clusters here, and we ended up with this number of slot coefficient. As you can see, for getting better intuition, you can see that HLB performs negative in terms of slot coefficient, but our work at least is less negative, or sometimes it's positive in terms of slot coefficient. Yeah, this was the experiments that I've done so far. You can see the codes, and I'm open for any contribution. You can use my GitHub repository for any contribution. Thank you very much.
Thank you, Ali. Thank you very much for the interesting presentation. We will keep the questions to the end of the session. I encourage everybody to use the chat. Thank you, Ali. And let's invite Xing Tan, which is the presenter of our second presentation today.
Thank you very much, and hope you're doing well. Thank you.
Thank you. I think Ali, oh yeah, you need to stop. You did it. Thank you.
Okay, go ahead. Go ahead.
Okay.
Oh,
thanks,
no.
Ali. Yeah.
Oh, Ali, you're still sharing, Ali.
If you have any question?
Oh no, the question, sorry. The question, you will have all the questions at the end of the session, okay?
Awesome,
so
thank you.
People can send the questions to the chat, or at the end of this session, I will invite all the presenters to turn off the camera, and then we address the questions of the audience altogether.
Thank you. Sure, thank you very much. Okay.
Okay, so let's go, Xing.
Wait a second. Let me first open the file. Okay. And then sharing my screen. Okay. So
Perfect. We can see it. Thank you.
all right, good. Thank you. I'm sharing the screen with the room. Let me now try the full screen. Okay, so good morning, everyone. My name is Grantham. I'm from NICASN University. The topic of my presentation today is complexity analysis of green pickup and delivery problems on ring structures. So the pickup and delivery problems is a variant to the classical vehicle routing problem. And this variant specifically needs to pick up some products or stuff and deliver it from one location and deliver it to some another locations. And we specifically started the problem on the task graph, which is under the ring structures. And the problem is also subject to the constraint of fuel tank capacity of the vehicle. And we provide complexity analysis with several intractable and tractable results obtained. This is a joint work with Jimmy Huang from York University and K. Huang from McMaster University. So before I go through the definitions and the results, let's first take a look at an example. The task graph at the bottom left. So this is a directed graph. We have nodes that are collected by age. And we can treat these 4 nodes, C, A, B, C, D, as 4 cities. And these nodes are collected with directed ages. So nodes are cities, and ages, each one of these ages represent a specific pickup and delivery tasks. For example, if we are talking about G2, which starts up from city B and enters city D, it means that 1 unit product would be picked up from city B and then delivered to the city D. So the problem of pickup and delivery for this specific example is that we have a shaded node CA, which is the depot city of the only vehicle in this example. And we need to find out a specific route where all these 8 tasks are actually achieved. And for each one of these tasks, the actual cost standing for the fuel consumption in order to achieve these pickup and delivery tasks is also listed here. For example, if we have T2, we see T22, which means that the fuel cost is 2 units when we achieve the tasks of T2. If we ignore the actual fuel consumptions in achieving these tasks, we will see that in finding out the feasibility for the vehicle to achieve these tasks are actually equivalent to the famous Euler-Toll problems, which can be solved in polynomial time, as long as the in degree and out degree of each one of the nodes are equal. We know that there exists an Euler-Toll for the graph. So if we ignore the fuel consumption, we see 2 example Euler-Tolls denoted as ET0 and ET1. So if we, take the ET0, Euler-Toll 0, we see that it contains 2 trails. The only vehicle that is based at CA will first go to T1 and pick up some stuff at city A, deliver to CB, pick up some another stuff and deliver to CD, and from CD to CA, so T1, T2, T3, the blue trail, the first part of the Euler-Toll ET0, and the only vehicle returns to the city A, the depot for the vehicle, and then it starts up the second trail, which is T4, T5, T6, T7, T8. So this is the second trail. And we might have another example like ET1. In these specific Euler-Toll, we see that the vehicle can go instead of T4, and then it returns to the depot right away. So T4, T8, and then T1, T7, T5, T6, T2, T3. So this is another example of Euler-Toll in solving these problems. However, we see that this problem is, in addition, subject to the constraint of the fuel tank capacity of the only vehicle. Let's say it is 8. And we know that for each one of these 8 tasks, they're associated with the actual fuel consumptions, like 224, 112, 11. It can be easily verified that if this fuel tank capacity constraint is further considered, only ET0 is the solution to the problem, because the first blue trail consumes overall 8 units of the fuel, which is less than or equal to the actual fuel capacity of the vehicle, 8. And the second trail, the purple one, added up, the fuel consumption is actually 6, which is also then less than 8. So it is actually feasible. However, if we try ET1, we see that the first trail, T4, T8, consumes 2 units. So it means that the next one would, the long trail would consume in total 12, which is infeasible. And the contribution of this work is to show that this problem in general and several of its constraints restricted versions are also intractable. So we are starting investigating these variants to the vehicle routing problems with specifically pickup and delivery tasks. And this is a green pickup and delivery problem because the fuel tank, the constraints of fuel consumption is further considered. So that's the example. Why we call this kind of additional constraint as green, because this problem is recently actively studied in the electric cars because of the limited availability of refueling infrastructures. This is the problem we study. Now, here is the outline. I will provide some definitions of the general GPD and its constraints, and I will use a figure to illustrate the complexity results and how they're related to each other, specifically a greedy algorithm that is used to solve a highly restricted version of the problem. Which means that restricted version is actually polynomial time solvable. And finally, I'm going to summarize this presentation. So we have seen that example. We know that when we talk about GPD, green pickup and delivery problem, it contains a 5-tuple C set of cities, T, so which are actually nodes, and a T set of tasks, which are actually ages. Remember that when we talk about one specific age, we have one unit entity that is picked up from one city and then delivered to the other. Each one of the age is associated with some weight or cost. We call it Fij, actual fuel consumption to achieve these tasks. And the set of V, in our restricted case, there's only one vehicle, so the size is 1. And the actual fuel tank capacity for this only vehicle. And the capacity of the vehicle is just good enough for 1 unit. So we also have a set of depot where the vehicle is based. So there's just one depot city and there's just one vehicle. This is according to our definition. We have already, present the problem in with multiple constraints already. So we have GPD superscript K, which means that in addition to the definition of the GPD problem, it is also required that the in degree and out degree of each of the node in the task graph is bounded by the some constant value kappa or K. Okay, so we have a GPDK. And then we have RIN with 2 parameters, delta and lambda. So in general, it is a green GPD problem, but the topology of the graph will form a RIN in one direction, either clockwise or counterclockwise. And then, so it involves multiple cities along the way, and the total number of cities is the second parameter lambda, and the actual total number of tasks between each one of the 2 cities defines the first parameter D. So we also call, after these specific topology structures of the task graph, we have the width of the ring and the length of the ring. So we have first parameter delta and the second parameter lambda. So for this specific example, we know that the D value is 2 because we see that there are 2 arrows between any 2 neighboring cities. And the lambda is 6 because we have in total 6 cities. So CA is shaded meaning that it is the only depot and the refueling station for the only vehicle. It means that maybe I forgot to mention in the example that if the node is shaded, it means that when the vehicle returns, it can refuel its tank to its full capacity. So that's the reason in that example, the only vehicle is capable to start up its second trail. Okay, that's the restricted version with 2 parameters: the depth, the width of the ring, and the length of the ring. And this is the figure that summarize. Am I running out of time? Oh, okay. So I still have some time, right? Okay. There's just like a few more pages. So this is the figure that summarizes the results we obtained. So it contains basically 3 blocks: the strongly NP-complete blocks and weakly NP-complete blocks, and the tractable area, polynomial time solvable area. And we have problems represented by non-rectangulars. And we have arrows. The direction indicates further restrictions. So we have GPDK. Now the degree is reduced to 2. And this is actually can be further restricted to ring 2 lambda, meaning that the width of the ring is 2. So this is a special case of GPD2. And we have general ring width and length. Now the length is reduced to a constant, and now the width is reduced to further restricted into some constant k to 3 to 2, and the length is further reduced from 3 to 2. And finally, like both the width and the length are actually constant. So we see that in general, NP complete strongly. And if the width is further restricted into some constants, they are weakly NP complete, meaning that there exists a shorter polynomial time using a dynamic programming to solve these problems. And finally, their polynomial time solvable. So the rectangulars in white are actually the results we obtained from one of our previous research published in AAAI. And for all these 3 gray rectangulars are the results that are newly obtained in this current paper. I have one content page actually that is a greedy algorithm for the algorithm that we proved the correctness of these algorithms to show that this ring delta 2 is actually polynomial time solvable. I'm not going to go through the details of these algorithms. Basically, we have 2 cities, multiple n tasks from left city to the right city, and n tasks from the right city to the left city. And we have, first of all, sort all these n tasks, and we have a for loop, okay, to like pick up one task from moving it from left to right, and then pick up another task from right to left. And we use mathematical induction to prove that if the problem instance is solvable, and then this algorithm will eventually find it. And at the same time, if these algorithm terminates with some positive with returns true, it means that, of course, these problem instance exists solution. So the correctness of the algorithm is actually rigorously proved, which is used to support our claims that ring delta 2 is actually polynomial time solvable. Okay, so time complexity analysis, it runs in big O n log n time. All right, so
yeah, perfect. Thank you. We need you to conclude. Thank you.
Oh, okay, so I am actually concluding. I'm going to go through these 2 pages very quickly. This research contributes to a better understanding of the computational property of the problems. We show multiple strongly and weakly NP-complete result. We use delta and lambda to describe the restricted version of GPD, which is rings. At times they're weakly NP-complete, and then from strongly NP-complete, it becomes polynomial time solvable. We believe that these set of results are going to be very useful when we are considering developing heuristics for solving these problems or design approximate algorithms for these problems. And finally, we are thankful to the reviewers for their feedback and suggestions. And this work was supported by the NICASN University, CERC, and NSERC for all the three authors. Thank you. This finishes my presentation. If I use more time, I'm sorry.
Thank you. No, thank you, Zhenyu. It's all right. We're going to keep the questions at the end.
Okay. I will.
Yeah.
Okay. Yeah, sure.
For those in the audience, I encourage you to use the chat if you have any questions, Xing, and then we address later.
Okay.
So yeah, let's invite Zhenyu Liao, the presenter of our third presentation.
Thanks, Renata. Let me share the screen. Yep.
Yeah, perfect. Thank you.
Morning, everyone. So today I want to talk about identifying significant edges for structural learning problem in Bayesian networks. This has been a joint work with Junyao, David Duan, and Peter van Beek from University of Waterloo. So first I want to talk about how it is used. The Bayesian networks is used as a data analysis tool in practice. So as you can see here, we have a wide range of applications using Bayesian networks. And very often they use the structures to identify relationships between the variables under consideration. And so the small n here is the number of features, and the big N here is the number of examples. As you can see, they can vary by a wide range. The C here is what we are what we are interested in here. So the C means the cutoff point for identifying whether an edge exists or not in the networks. So as you can see, the cutoff values varies widely between applications. So it's often been picked up as an ad hoc value without much consideration or deliberation on why that value was picked in the experiment. So essentially, yes, this is how we want to tackle. So the problem is how to set the threshold for identifying the edges. Previous approaches, we have three previous approaches here. The first one is the permutation test. The premises of the permutation test is that if the data is randomly generated, then we should have, then all the edges identified with a randomized data set would be like non-existent or spurious edges that shouldn't be there in the golden network. So that's the premises of the permutation test. The second one is the minimizing L1 norm. So this is theoretically a more sort of pleasing approach, and it is the default approach in the BLearn package for identifying edges. And we prove in this work that it is actually turns out to be a constant threshold, which corresponds to 0.5. It's not necessarily a bad conclusion because 0.5 is actually corresponds to a balance between precision and recall. I will talk about it later in the presentation, but it's actually a balanced sort of decision there. The third approach is called the stochastic process. So what this models is that essentially each edge can have 3 actions at each step. So it can be like an edge from one node to the other, or the reverse edge from the other node to this node, or no edge at all. So those three steps are modeled as a stochastic process in this work. Although we have like three previous approaches, there's no comparison among those three. And we aim to sort of fill that gap there as well. And here we also have our own considerations for how we should set up the threshold. So our threshold is essentially, we model it as a transfer learning problem. We first transfer the edge setting problem to a supervised problem. So we use the ground truth networks as the label. So the ground truth network can either be the real Bayesian networks from the BNN, or it can be the best scoring Bayesian networks learned in the real world dataset from UCI repository. And the data we use is essentially the probabilities on edges. So using the dataset, you can learn a set of like plausible networks, either through bootstrap or through credible set. And through the set of networks, you can get the empirical frequency of the edges. So the empirical frequency it means that is what we call the probabilities here, and that is used as the data to the supervised learning problem. And how do we do transfer learning here? So we have a source domain from a bunch of proxy Bayesian networks and their data, so their probabilities. So if we have we can find the best threshold that optimizes a given metric, and then we use this threshold on the target domain. So the target domain is the Bayesian networks of interest. And then we apply the same threshold to identify the edges in the target domain. And that is our proposal here. So to evaluate our proposal together with all the previous approaches, we use both the datasets from BNN and UCI datasets. The BNN datasets, as I mentioned before, is a collection of ground truth Bayesian networks of various variable sizes. And we generated samples ranging from 50 to 10,000. And we used 10 ground truth Bayesian networks from this repository. For the UCI datasets, we also applied the Kiang imputation for missing values and supervised discretization for continuous variables. And then we learned a single network using the 4 scores separately. So in the end, we have like 16 UCI datasets, and then the 4 scores under our consideration, AIC, BIC, BDU, and QML. And in the end, we have like 64 Bayesian networks. So that those are the best scoring Bayesian networks with each score using in each dataset. So here's the range of datasets under our consideration. And you can see that it's of various sample sizes, and the variables range, the number of variables also range from 10 to 76. So that is all the datasets we use in our experimental evaluation. And we also have metrics to consider. So as I mentioned before, the transfer learning problem, we are trying to optimize a given metric on the source domain. So we have 2 metrics. One is structural Hamming distance. This is a Bayesian network's specific metric. Approximately, this metric is the sum of missing extra or reversed edges. And this is cost insensitive in the sense that the missing extra or reversed edges are treated as equally punitive in the metrics. So there's no reweighting there. The second metric we consider is F beta measure. So this is a weighted measure, so between the precision and the recall. And this one, we call it cost sensitive measure, because you can choose your own preference about precision or recall. And to aggregate our results, all the data sets, we use a border count. So border count, here's a small example. So on each instance, we assume that the large metric values are better, and each score is awarded points depending on their relative ranking with respect to others. And the points are summed up for each score. So here, as you can see, the metric value, QML has the highest metric value, so it's awarded 3. But Beek and BDU, they are of the same score, so they are each awarded 1 because they are ranked higher than AIC only. And the lowest ranked score always gets 0. So this is our results on structural Hamming distance. So the comparison of the previous 3 threshold setting approaches are also presented here. So permutation test, minimizing L1 norm, and stochastic process here is presented here. And the machine learning one is our proposal. And as you can see that our proposal outperformed the previous approaches on both the credible set or the bootstrap approach. And this one is our evaluation on the F beta scores with various betas. So beta, again, is your preference between precision and recall. And here you can see that so our machine learning approach outperformed the previous 3 proposals. So this is the experimental results. We do have some additional results in the paper. For the time constraints, I omitted to not show here. So the conclusions. So we have proposed a transfer learning approach that is significantly better than previous approaches on setting the threshold. And the evaluation is essentially based on a wide range of data sets with the 4 popular scores that are used in today's Bayesian network structural learning study. And we also so this scheme, because it optimizes a given metric, so it allows for any given metric, especially the cost-sensitive one, to be incorporated in threshold setting as threshold selection process. And we also want to stress that based on our study here, people in practice need to make an informed decision about their threshold. Because if you are drawing conclusions from an arbitrary threshold, then the conclusions might not be that sound from the previous papers in practice. And thank you for your time. We'll reserve the questions in the end.
Thank you. And right on time. Thank you very much for that. Do we have someone from the 4th presentation on theoretical connection between local linear embedding factor analysis?
Yeah, that's me.
Oh, okay, go ahead. So you have 8 minutes, okay?
Yeah.
Thank you.
Let's get this shared here. Okay. Can you see my screen?
Yes, thank you.
Great. Okay. Okay. So yeah, I'm Mark Crowley. I'm associate professor from the University of Waterloo. So pretend that my slides have the same format as the previous presentation. So we got the logos everywhere. This is joint work with Professor Ghodsi and Fakhri Karray in the Waterloo as well, different departments, but mostly work from student Benyamin Ghojogh during his PhD on dimensionality reduction. This is kind of one of his contributions. He's now working, so couldn't make it here. I wanted to, I'm also on the national board for Kayak, which kind of organizes and like arranges at least the events of this conference happening. And I wanted to remind everyone your papers all have a PubPub website connected with it, right? For the AI conference. And those papers even have a very nice discussion section at the bottom. So I encourage everyone to go on to the one for our paper, but also for everyone's papers. And you can have questions, comments there and keep the conversation going. So, So this just short kind of taste of what the paper does. We were just doing a theoretical kind of observation here and some proof about a couple methods in dimensionality reduction. So what's dimensionality reduction? So this was the entire topic of Benjamin's thesis. And we're doing a textbook on it actually coming up later this year. And the idea is you have a lot of data and you want to make it smaller so that you can do things either more efficiently or more compactly on an embedded machine, or sometimes it's even just that the features are better, right? So everyone uses this at some point. If you've ever used PCA or LLE or TSNE visualization, there's so many methods that are actually dimensionality reduction or manifold learning, feature extraction. There's lots of different names for it whenever you're doing a projection to some smaller space, right? The idea though is always, no matter what it is, you're looking at the data as a whole, looking at the kind of features you have, trying to come up with a lower dimensional representation of those features and using that instead, right? So obviously, deep learning does a lot of this kind of implicitly in some of its implementations, but there's lots of methods for doing this on its own beforehand, of pre-processing or other methods. So what we did in this paper was to kind of make some observations about a few types that are really a little bit different, but actually showing how they're basically very tightly related. So we divide dimensionality reduction to kind of three broad categories: spectral methods, which you might be familiar with PCA, eigenvector methods, things like that. Probabilistic methods, like factor analysis, where you're kind of coming up with weighted vectors and using probability distributions to come up with a more compact representation. And then neural network-based methods that like autoencoders and that kind. So we're not talking about that third one, but we've made some observations about the connection between these spectral and probabilistic methods. So essentially we're building a bridge between these three methods, so factor analysis, probabilistic PCA, and LLE, and kind of reformulating them to be all kind of in the same format, and then showing how that helps explain some of the behaviors and different properties of them. So it's kind of an interesting, connection between them, but also potential for other types of things like this between other methods. Not that there has to be one unified, dimensionality reduction model for everything. I don't think there could be, but a bunch of them have a lot of things in common. So I'll go through one or two of them at very high level. On the paper, we go through in more depth, so you should go there and look at that. So factor analysis, this is a graphical model representation of what factor analysis does in our view. Essentially what you're doing here is projecting your data set from some set of features D to a smaller set of features S, say, and you're trying to come up with a transformation that will get you there. And so the way that can be represented is in factor analysis is we come up with a linear transformation, right? So we've got a transformation matrix lambda that can be used to transform the data into a different number of dimensions. And then there's also a noise component. So in factor analysis, you have this Gaussian noise component with an assumption that the correlation, the covariance matrix of the noise is basically diagonal. So it has independent noise for all the different factors. And the idea is that you're proposing that there are latent variables that explain, all the correlations and pattern in the data. So that's that formulation where you recast it in this way. Probabilistic PCA is a generalization of standard PCA, a kind of eigenvector analysis that some of us were talking about at dinner yesterday. And obviously it basically adds probabilistic, basically non-zero noise to some of the dimensions and mappings. So PCA is just probabilistic PCA with no noise. What we were showing in this paper or connecting to is also that factor analysis can actually be seen, PPCA can be seen as a type of factor analysis where the noise is just equal in all dimensions, whereas factor analysis, it could be more diverse. And so we basically get the same formulation and kind of tie them together. And then LLE is a quite different method where you're trying to find linear reconstructions of a generative representation that kind of takes your data and generates a new representation that is smaller. But we can formulate that in the same way where there's this transformation matrix X. And what did we do with this one? There's a difference with that from the lambda because it has a different property, but we also have to have the covariance matrix for this one has to be solved. So what we were doing here was saying, if you cast it this way that it's seen as a transformation matrix like the other two, you have to solve for this, what the covariance matrix would be, but you can do that with EM, and that's essentially what the LLE algorithm does if you look at it the right way. And then, so essentially now we can look at all three of these essentially in the same form, where this matrix is a little bit different. And the observation we're making is that the matrix for factor analysis in PPCA is data dependent because it relies on is data independent. Sorry, I was seeing that. I was thinking, it doesn't matter how many data points there are, right? It's just using the features directly, right? Whereas LLE, the mapping is kind of localized to the data points themselves. And so they have this scaling. So they have very similar pattern and noise and structure. And yet LLE is a nonlinear approach and the other two are linear. And so this kind of explains why. And it's just a nice kind of way to connect a bunch of them together. And yeah, so that's the high level idea. And if you want to find out more, go read that paper, and go read everybody's papers on PubPub and talk about it there. And I think the research funding we had for this came from NSERC and NRC on various different programs. Some of the applications we were doing for dimensionality reduction, a lot was on medical imaging, which was an NSERC grant we had, where we had very large medical digital pathology images and trying to find lower dimensionality representations of that. So that grew, inspired a lot of this kind of research. Yeah, and we have citations there, but you can see that in the paper as well. So I'll wrap up there, and if there's questions after, we can have it.
Thank you. Thank you very much, Mark. And let's go to our last presentation. We also have 8 minutes on generative enriched sequential learning.
Hi, sounds good. Let me try to share my presentation and let's see if this works.
Yeah, perfect.
Look good. All right, perfect. Thank you so much. All right, good morning. My name is James Nguyen. I'm a research officer at National Research Council of Canada. And I would like to thank the conference committee for the opportunity to present our work around quantum enhanced design. And the title of this talk will be Generative Enriched Sequential Learning Approach for Molecular Design via Augmented Domain Knowledge. So the discovery of new materials can be an expensive and time-consuming process. And using machine learning in a hybrid approach with quantum computing capabilities could potentially improve the prediction and the speed of which new materials can be discovered. So in particular, this project tries to explore quantum computing as a new way to generate high quality data set for machine learning workload. So in this presentation, I'm going to talk about mostly machine learning and a couple of things with quantum computing that worked or did not work for us. It's kind of a learning process for us and an ongoing project as well. But in general, we use objective functions such as quantum estimate of drug likeness scores or SA scores to evaluate those generated molecules, for instance, and also to use quantum chemistry calculation for us to select best-in-class molecules based on the objective that we want. And also we explore a couple of quantum simulations using Qiskit on IBM Quantum Experience as well. So this is an overview of our machine learning framework. We call it the Enhanced Sequential Learning, or the ESL framework. At the heart of it is the ESL that is being trained on the QM9 data set. So QM9 data set has about 134,000 stable organic molecules. So this is a unsupervised training in the first pass so that we are able to generate some new molecules based on sequential learning. Now, having done the first pass and generating a couple of thousands of these molecules, we feed them to quantum chemistry calculation so that we can understand, ground state energy, force field energy, and things like that. And with the properties that have been calculated, again, we select for, best in class molecules again, and then feed them back to the ESL for iterative training of the model. Excuse me. At the heart of the ESL is a recurrent neural network, which I will talk a bit more in the next slide. Excuse me. So the recurrent neural network essentially is pretty basic, but lack of the memory and has the vanishing gradient issues. So in practice, we use something called LSTM in order for us to learn the long strings in which the chemical properties are being made up of. After generating these molecules, we actually run them through a few quantum chemistry calculation. Originally, we wanted to run variational quantum eigensolver on a quantum computing environment. That's, in theory, is most accurate method to do so, but in practice, we couldn't scale beyond diatomic molecules. However, we do try some other methods such as summation function to compute the energy of a larger molecules, for instance. So in practice, on our workstation, we still are able to calculate Hartree-Fock, for instance. It's quantum compatible, but the energy calculation can be done reasonably well and accurate enough that we can use it to be validated against some database. So we use tools such as OpenBabel and PySCF for this calculation. We also did a universal force field calculation as well. It's least accurate, but it's pretty fast. So we can actually calculate a lot more molecules with it using a classical method. So this is the first set of results that we have. Using unsupervised learning on a QM9 dataset, the QED score is pretty low. So the larger the QED score, the better it is, more desirable the molecule it is. Subsequently, the first and second set of training, we can see some improvement. And then after we select some of the molecules based on the properties that we want and retrain them, we managed to reach a much higher QED score using this method. Finally, we want to try to understand if there's some sort of correlation, if a lower ground state energy correlates to higher QED score. But it turns out that that's not really the case. And we try to find a numerical difference between the universal force field and also the Hartree-Fock energy. And we managed to see some patterns, some clusters coming out of it. As I've highlighted in this figure here, there seems to be some sort of design principle there that actually confer to higher QED score, if you will. So this is one of the figures that sort of show there's some sort of design principle. On the left are very poor QED scores molecules, and on the right are much higher QED scores molecules. And we can see really quickly that there seems to be some sort of design principles in the sense that there are rings that in molecules that has higher QED score. So we hope that in the next step, we are able to generate molecules with certain properties using a quantum computing environment and develop enhanced training data set and keep improving the sequential learning framework. Iteratively, we want to also evaluate the novel molecules of QED with assay score as well. So assay score is a different score. However, there's lots of challenges. The retraining depends on large chemical structure data set. There's a lot of invalid chemical structures as well. Quantum chemistry calculation on our workstation are time consuming. But moving to a quantum computing environment like IBM is a little limited to the size of the molecules that we can calculate. With that, I would like to acknowledge the team that has been working on this, Dr. Sajjad Ghaemi, Karl, Isaac, and Dr. Yifeng Li. With that, I'm going to conclude. Thank you, and I'm happy to take any questions.
Thank you very much. Thank you very much for your presentation. We are actually 5 minutes out of time, but if it's okay for the presenters, I would like to give a chance if someone has an urgent question, maybe one or two, but I really like the tip from Mark that we have on the conference, all the papers that we have a comment session, so questions can also be addressed there. So just going through the audience, do we have any question that you'd like to address right now? I definitely have some, but I will try the comments on the papers. That sounds interesting.
I have a general question, if it's possible to ask. For dimensional reduction techniques like PCA, I guess the first assumption is that how many principal components we have already. What is the best approach to find the optimum number of principal components? And I guess for clustering application on top of this PCA method, we need to apply one clustering method on the results. So which one is the most common technique that we can use? And not as a general case, I mean, which method is most common in the literature for clustering the results of PCA?
Mark or Ali?
Yeah, anybody can ask. I could answer a little bit, just how many components. I would say there's no right answer. It depends on what you need, right? Like all of the PCA is essentially just computing the eigenvectors of your data. So you have as many as there are dimensions in your data, but most of them are not useful. We were having discussions last night about some people, if your data is time series and you're in physics, maybe you only want the 0 vectors, but in data, we usually want the largest vectors because they explain the most variance. So it depends how many dimensions you need for your reduction, right? So it's really dependent on that. You usually can get a bit of diminishing returns. So people do these skew plots where you see like how much reduction in variance you get, explanation of variance you get for each vector, but it depends on the data. Maybe Ali, if you want to ask the second part, I don't know.
Ali, you had working with clustering. Do you want to address the clustering question?
Yes. In fact, after doing dimensionality reduction, I believe the number of components that you use is highly affects the result of clustering. And of course, the way that you do the dimensionality reduction, I don't know about the PCA, but I believe that it is for the orthogonal data sets where you're using non-orthogonal data sets. You have to use ICA, which is an improved version of PCA. So I would propose to, I don't know who was the asker, to use ICA instead of PCA if you want to get the better clustering results.
Yeah, I asked the question. I already used ICA. On the ICA, we have the same assumption. The first is that we need to assume that the data distribution is Gaussian or non-Gaussian, is based on the PCA or ICA, but still there is one question that how many ICs then we have to select at the beginning. So,
well, it highly depends on data and their correlations to each other. We cannot say that the specific number of components would give you the best result. You can do a grid search or random search to find the best components in that case.
So I asked this question because the reviewers always ask this question in publications. So how you found the optimum number?
The best way is doing grid search or random search.
Random.
You can do that.
Okay.
You need to justify it, but there isn't a right answer. They're not asking you the right answer. You know how you did it. Yeah. And same with
Thank you.
clustering, right? You could use k-means or dbScan, like density-based ones, but there's different clustering algorithms that have different properties. So you can't just pick one either. It depends on what you're doing. And it's dangerous to commit to one just because it's the best, I think.
Okay, thank you so much.